Question 4 is really about ionic equation practice. So we've already used ionic equations quite a lot this year, particularly in the redox stuff that we did earlier on. But they're going to be completely dominant in this stuff in acids and bases, and actually also in transition elements, which is yet to come. So if you're still not really comfortable with them, now is the time that you've really got to do that. And that's what this question is about. So the first one is calcium hydroxide solution and ethanoic acid. So calcium hydroxide, Ca2 plus and OH minus, so that's the formula, and that's aqueous, plus ethanoic acid, which it doesn't specify. I mean, if it was the pure substance, that would be a liquid, but it's going to be aqueous once it mixes anyway, so let's call it aqueous. And we just get the general reaction. Acid plus alkali goes to salt plus water. So the salt, remember, we're going to have ethanoate ions left behind when H plus is donated from there. So that's just a 1 minus ion, which has got to pair with the calcium 2 plus. So we get that as our salt. Okay, to balance that up, and that means that we're going to need 2 of those, and that gives you 2 waters as your other product. Okay, so it's just acid plus alkali goes to salt plus water. Now, what we then have to do is write that as an ionic equation. So we'll go through this one fairly slowly, and then I'll just do the others much faster, but it's always following the same recipe. So remember that the thing about ionic equations is that you only write the ions separately if they really are separate. So it's not a trick that we're doing here, it's about representing more precisely what's going on in a solution. So when you have an ionic substance like calcium hydroxide, you know that once you dissolve that, the calcium ions are no longer stuck to the hydroxide ions because they all become separate, interacting with water through ion dipole forces. And all we're doing in an ionic equation is reflecting that by writing the ions separately. So you will only do it for an ionic substance if it's aqueous, not if it's solid. So it is aqueous, so we write them separately. Ca2 plus 2OH minus. Now when we come to acids, there's a complication because some acids are strong, which means they're completely broken up into ions. Some acids are weak, which means only a part of the population is broken up into ions. So you think, well, do we write them separately or don't we? But the convention is just write the ions separately, because if it's an acid, then some of them, at least, are going to be broken up into separate ions. Some of the molecules are going to be ionized. So with acids, in ionic equations, you just write the ions separately. So 2 moles of ethanoic acid will give you 2 moles of ethanoate ions plus 2 moles of H+. Okay, so both of the things on the left-hand side in this case are aqueous, broken up into ions, at least to some extent, so we write them as separate ions there. On the right-hand side, this is still an ionic compound, so again, if it's an aqueous solution, we write the ions separately. So we have 2 CH3COO minus, and we have calcium 2 plus. Water, on the other hand, is a molecule. Almost no water, not exactly no water, and that's something we'll look at later. A tiny, tiny bit of it is broken up into ions, but so small that we ignore that for these purposes and say, right, water is just molecules. So we don't write them as separate ions because they're not, and so we write it like that. So it looks a mess, but that is before we look at the fact that some of the ions that were there at the beginning are still there at the end, and that's the beauty of ionic equations, that they then get edited out. So you can see that the calcium ions were floating around in the solution at the beginning separately, and they're still floating around separately at the end, so they just cancel out because they didn't actually change in any way in the reaction, so they shouldn't really be there. And the same with the ethanoate ions. We've got 2 moles of ethanoate on the left, 2 moles on the right, so again they didn't change in the reaction, so they cancel out. And what you're left with is therefore 2OH minus plus 2H plus goes to 2H2O. Which looks much simpler, but actually we still can't quite leave it there, because remember that equations should always be in their lowest terms. That means that if you look at all the balancing numbers, if you can divide them all by 2 or by 3 or by anything and still get whole numbers, then you should do that, because they might just mark it wrong if you leave it as a multiple like that. They don't always, but they do sometimes. So you divide through by 2 and get this as your simplest form of the equation. And you can see that's extremely revealing, because it means that what appeared to be quite a complicated process when you write the full equation is actually incredibly simple. That all that happens is the hydroxide ions accept the protons. In other words, they bond to the protons, forming a dative covalent bond, as we said, to form water. And that's the only thing that actually happens in that reaction. That's why ionic equations are so good, because they simplify things and they let you focus on what's really changing, rather than just being a balancing exercise. So next we have iron 3 oxide and sulfuric acid. So iron 3 oxide, it doesn't say solution, so it's not in a solution. It would tell you if it was, plus sulfuric acid, but you assume with these inorganic acids that they are in aqueous solution. So this is not going to be separate ions, because it's a solid. So iron 3 oxide is Fe2O3, because 2 lots of 3 plus will balance 3 lots of 2 minus. So it's Fe2O3. And that's a solid. Sulfuric acid is H2SO4, and that's aqueous, and it's going to give you a salt, which will be iron 3 sulfate. So again, if you're not sure about the formulae, just think about the charges on the ions. You've got Fe3 plus is the iron, and sulfate is SO4 2 minus. So don't just guess, just write the ions down and think, oh yeah, to balance those up, I need 2 lots of Fe3 plus and 3 lots of sulfate. So you get Fe2SO4 3 aqueous plus, again it's acid plus oxide goes to salt plus water, so you're going to have water, which is a liquid, and it's just about finding the right numbers of waters to balance it up. So you can see the ions are already balanced. So 2 there and 2 there. So that means we need 3 sulfates. So that's got to be a 3 in there. And then if you add up the hydrogens and oxygens, you've got 6 hydrogens, 3 oxygens left. So 3H2O. When it comes to the ionic equation, as we already said, ions are not separate in Fe2O3, so we don't write them separately. It's still Fe2O3. But this is an acid, so it's broken up into H plus ions and sulfate ions, at least to some extent, but we ignore the some extent bit and say, right, if it's an acid, we write the ions separately. So you can see we have 6 H plus, 3 lots of 2, plus 3 sulfate ions. This is an ionic substance and it's in solution, so we've got 2 Fe3 plus, and then separately 3 sulfate ions. Because they're in solution, they're separate. It doesn't tell you in the question that this would be formed in solution, so you might think, well, how do I know it's not a solid? But the answer is that you assume that these ionic substances are soluble when they're formed in reactions, unless it's one that you know isn't. So for example, if it was something like silver iodide, which you know is insoluble from the silver tests, or magnesium hydroxide, which you know is insoluble from the group 2 stuff that you've done, in those instances you wouldn't put aqueous because you know it's insoluble. But most ionic substances are soluble, so you assume solubility unless you know otherwise. So that's your iron 3 sulfate, and then water, as we already said, is just water, it's just a molecule, so you just write it like that. Do your cancelling, which this time is just the sulfate ions, because everything else changes. The iron 3 ions were locked into the oxide here, but they're not anymore, so it does need, they do change, so they do appear in the final equation. So Fe2O3 solid plus 6H plus goes to 2 Fe3 plus 3 waters. Okay, and that's your ionic equation. Right, so then we have solid barium carbonate plus hydrochloric acid. So barium carbonate is BaCO3 and hydrochloric acid is HCl aqueous. And so we're going to get barium chloride. Acid plus carbonate goes to salt plus CO2 plus water. Salt will be barium chloride, which is BaCl2, because barium is 2 plus being in group 2, but chloride is only 1 minus. So think about the charges on the ions, make sure you get the formulae right. Plus water plus CO2, that's following the normal pattern of acid plus carbonate, and you can see to make that balance that needs to be a 2. And then for the ionic equation, barium carbonate is still barium carbonate, but HCl is broken up into ions because it's in solution, whereas the barium carbonate wasn't. But the barium chloride is, again, we assume that it's soluble because we've you may not know that it is, but unless you know it's insoluble, then you assume it's soluble. So we're going to have Ba2 plus aqueous plus 2Cl minus aqueous plus water is a molecule plus CO2 is a molecule. Okay, do your cancelling. This time it's the chloride ions. Everything else changes. And so you get barium carbonate plus 2H plus gives you barium 2 plus aqueous plus water plus carbon dioxide. Aqueous potassium carbonate, K2CO3, 2K pluses, balance CO3 2 minus, plus nitric acid, which is HNO3. Again, for these acids, it doesn't always say aqueous, but you have to assume that they are. So acid plus carbonate goes to salt plus CO2 plus water. So we're going to get potassium nitrate as the salt, K plus, NO3 minus. So 1 plus 1 minus, so it's just KNO3 aqueous plus CO2 plus water. And you can see, because we're stuck with 2 K pluses there, we're going to have 2 KNO3s. That means we need 2 nitrates. So that's going to have to be a 2 as well, and then the CO2 and the water balance it up. So that's your full equation. When it comes to the ionic equation, it's all in solution here and here and here. So lots of separate ions. So 2K plus carbonate plus 2H plus 2 nitrates. So lots of ions in that cocktail on the left hand side. Separate ions again here in the product because that's aqueous compound, so 2K plus 2 NO3 minus plus CO2 plus water. So lots of cancelling to be done because the K plus ions didn't change. Sorry, that should have been aqueous. They didn't change. The nitrate ions also were there at the beginning, still there at the end. They didn't change. So what you're left with is carbonate plus 2H plus goes to CO2 plus water. And that's your ionic equation. And again, you can see how much more general that is, because it doesn't matter if it's potassium carbonate or sodium carbonate or lithium carbonate or whatever. I mean, any soluble carbonate reacting with any acid. Here it was nitric, but it could have been sulfuric or hydrochloric, and this ionic equation would have been the same. That's why they're so good, because they're much more general and they're much more directly telling you what really happened in the reaction. Aqueous ammonia and sulfuric acid, aqueous NH3 plus sulfuric acid. And again, make sure you know the pattern. So these reactions are particularly simple because all that happens is the H plus ions from the acid are accepted by the ammonia to form NH4 plus, which then, if you like, complements the negative ion that's left behind. So there is only the one product, which is the salt. So acid plus ammonia, or indeed acid plus amine, goes the same way, just forms a salt, no other product. So the salt will be ammonium sulfate. So we need 2 lots of NH4 plus to balance the 2 minus on the sulfate. So that will be the product, ammonium sulfate. Okay, and that obviously just needs a little bit of balancing, 2 ammonias to balance up the 2 ammonium ions there. And then we can write that as an ionic equation. So ammonia is just ammonia. So that's essentially just a molecule. But this is broken up into ions. So 2H plus sulfate. And this is an ionic salt. So again, broken up into ions. So 2NH4 plus sulfate. So long as the ions are in aqueous solution, you write them separately. And the cancelling in this case is the sulfate ions. So you get 2NH3 plus 2H plus gives you 2NH4 plus, and that's your ionic equation. But as we had in an earlier example, you have to notice all those 2's and realise that you can simplify that further by dividing through by 2 and ending up with the even simpler equation. NH3 plus H plus goes to NH4 plus. And you know, that shows now directly what we said at the beginning that we sort of inferred from this equation, but that makes the point directly that that's all that really happens, is the ammonia molecule uses its lone pair to form a dative covalent bond to H+, and that's the only thing that happened in the reaction. So methylamine and hydrobromic acid. Methylamine is that, as you know, plus hydrobromic acid is HBr. And remember, when we learnt about amines, we learnt that the simplest way to think about their acid-base chemistry is that whatever ammonia does, amines do too. So it's going to be the same kind of reaction, that the amine with its lone pair on the nitrogen can just pick up a proton from the acid and form a salt. So all we're going to do is form methyl ammonium chloride, bromide rather, which is going to be that. And that's the equation. Balances straight off, nothing more to do there, so we can go straight to the ionic equation. Methylamine is just methylamine. Okay, it's not itself broken up into ions, so that's that. But HBr, like any other acid, we write the ions separately. And this is an ionic salt, so if it's an aqueous solution, again, we write the ions separately. And the bromide ions are spectators, and so you end up with this. When you've done loads of these, you may get to the point where you don't really need to write this intermediate stage out, where you can see what the spectator ions are going to be straight off, and that's fine if you're very confident that you've done that right. So we end up with essentially the same story for an amine, and it could be a primary or a secondary amine because it's the same story for both, that they just do what ammonia does. One molecule of the amine picks up one proton and forms the ammonium ion analogue, so you would call that a methyl ammonium ion. So it then asks us about magnesium and sulfuric acid. Now it's really important that you realise that this is a different sort of reaction. It often gets lumped together with the acid-base reactions because obviously it involves an acid. But if we write the equation, so we have magnesium plus sulfuric acid. So acid plus metal goes to salt, which will be magnesium sulfate. So it makes a salt just like the other reactions do, plus hydrogen. And that's your reaction, and it just balances straight off. But the reason it's different is you can see that the H plus ions from the acid haven't just been accepted by a base, they haven't just accepted a pair of electrons from something and jumped onto it, like accepting a pair of electrons from OH minus and jumping onto it to form water. They have actually been reduced to form hydrogen. So this is different. It's not an acid-base reaction, it's a redox reaction. So you've got to make sure you remember that, because sometimes you get asked, what kind of reaction is this? And when you see the acid, people will say, oh, acid-base, but it's not. It's a redox reaction. So just to make that point, we'll have to find the oxidation states. First we should do the Ionic equation. So magnesium is just magnesium, but here the acid is, as we know, broken up into ions. So we've got this. The salt is also aqueous, so it too is broken up into ions. But the hydrogen is just a molecule in the gas phase, so it's just H2. And you can see that the sulfate ions we forgot there. Those are there as well. So now you can see, now that we've written them in, that the sulfate ions are spectators, because they were there at the beginning and they're still there at the end. So those drop out. So that tidies up to give us Mg plus 2H plus goes to Mg2 plus H2. And you can see that it's somehow much clearer then in that equation that it's a redox reaction, because the magnesium is losing electrons to form Mg2 plus, the H plus ions are gaining electrons to form hydrogen. And so it leaps out at you that it's a redox reaction there in a way that possibly it doesn't so much with the full equation. Yet again, that's why ionic equations are good. We can back that up further though just by using oxidation states, and you can see that when magnesium is an element it's 0, because that's what elements are, but it becomes plus 2 when it's a 2 plus ion, so it gets more positive and therefore is oxidized. But H plus starts out as plus 1 but ends up as 0 because it becomes the element. So it's going from plus 1 to 0, so it's getting less positive and therefore is reduced. Right, question 5 then is a strong acid, weak acid question. So we've got these two related acids but with these very different properties, that this one is weak, this one is strong. So first of all it asks us to explain what that means. So a strong acid, the definition of that in words is that it is completely ionized in aqueous solution. So what does that mean? Well, it just means that essentially every molecule, or it's never going to be quite every one, but very, very nearly every molecule is broken up into H plus and the rest. So we can express that as an equation by making it a one-way equation and saying when you dissolve that in water, all of it breaks up to make CF3COO minus plus H plus. Okay, and that one-way arrow saying that essentially all of it gets converted into ions, that's saying that. So ethanoic acid is a weak acid, which means that it's only partially ionized in aqueous solution. In other words, only a fraction of those ethanoic acid molecules are actually broken down into ethanoate ions and H+. So in a solution like vinegar, which is a dilute solution of ethanoic acid, most of the molecules are floating around still as that, and it's only a small fraction of them in that case actually which are broken up. And of course we can express that in equation form by putting a reversible sign into the equation. So we've got ethanoic acid reversibly giving you ethanoate ions plus H plus. Okay, so that's the bit that you've absolutely got to be confident about. But it also asks you to suggest an explanation. That's a bit more speculative. It's something they would be much less likely to ask you to do, so don't worry so much about that. But a good way to think about it is to think, well, what determines how far over to the right this is? In other words, how much this reaction happens is how stable the negative ion is, because you can see that's the big difference between the two, that we're creating negative ions which are different from one another, whereas the H plus ions are the same. So it's the relative stability of those ions that's the key thing. So if we compare those two, in CF3COO minus you have a negative charge obviously, but the size of that negative charge, or the extent to which it's localized on the oxygens, is decreased because you have these three very electronegative fluorines. Remember, fluorine is very good at attracting electrons in a covalent bond, so it will pull electrons away, or all three of them will pull electrons away from that carbon that they're attached to. So that carbon in turn becomes very delta positive and pulls electrons away from this one, and this one in turn will then tend to pull charge away to some extent from the oxygens, and so basically the size of the negative charge on the oxygens decreases, and spreading out the charge like that helps to make it stable. Whereas in ethanoic acid, these hydrogens are not going to do that, because hydrogens are less electronegative than carbon, so they're not going to help at all in pulling the negative charge in that direction. So you have a bigger negative charge left on the oxygens, and that's what makes it less stable. So that's the underlying explanation, but as I say, don't worry so much about that. It's making sure you understand what weak and strong acids are. That's the really important bit.